In the endless, inky blackness that followed the Big Bang, the universe was a very different place. It was a vast, dark expanse, filled mostly with hydrogen, helium, and a mysterious substance we call dark matter. For millions of years, there were no stars, no galaxies, not even a single glimmer of light to break the monotony of the cosmic dark ages. Then, something incredible happened. The first stars, known to astronomers as population 3 stars, ignited, bathing the young universe in its very first light. These were not like the stars we see in our night sky today. They were titans, behemoths of unimaginable size and power, hundreds, perhaps even 1,000 times more massive than our own sun. Their lives were brilliant but brutally short, ending in cataclysmic explosions that forever changed the course of cosmic history. But what fueled these first cosmic giants? What was the secret ingredient that allowed them to form and burn so brightly in the primordial soup of the early universe? The story begins with gravity, the universe's master architect. In the aftermath of the Big Bang, the universe wasn't perfectly uniform. There were tiny, almost imperceptible fluctuations in the density of matter. These minuscule variations were the seeds of everything that would come. Gravity, relentless and patient, began to pull matter together in the slightly denser regions. The primary ingredients were simple: hydrogen and helium, the lightest and most abundant elements forged in the Big Bang's fiery crucible. But there was another, invisible component at play: dark matter. While we can't see it or interact with it directly, dark matter makes up about 85% of all matter in the universe. Its gravitational pull is immense. It was dark matter that formed the initial scaffolding of the cosmos. It clumped together first, creating massive, invisible structures called dark matter halos. These halos acted as cosmic wells, their immense gravity drawing in the ordinary matter, the hydrogen and helium gas that was scattered throughout the universe. As the gas fell into these dark matter halos, it began to compress. Imagine squeezing a bicycle pump. The air inside gets hotter. The same principle applied here, but on a cosmic scale. The gas clouds grew denser and hotter as gravity continued its work, pulling more and more material inward. This process wasn't quick. It took millions of years for these clouds to accumulate enough mass. Inside these collapsing clouds, a battle was being waged. The inward pull of gravity was fighting against the outward push of gas pressure. For a star to form, gravity needs to win. This is where the secret ingredient comes into play, and it's something surprisingly simple: molecular hydrogen. Regular hydrogen in the early universe existed as single atoms. However, for the gas to cool down effectively and allow gravity to take over, these atoms needed to pair up and form molecules, specifically H2. Molecular hydrogen is an incredibly efficient coolant in the cold, metal-free environment of the early universe. When two hydrogen atoms collide and form a molecule, they release a tiny bit of energy. This energy escapes the cloud, carrying heat away with it. This cooling process was absolutely critical. As the cloud cooled, the gas pressure dropped, giving gravity the upper hand it desperately needed. Without the cooling effect of molecular hydrogen, the gas would have remained too hot and pressurized, resisting gravitational collapse. The formation of the first stars would have been stalled, perhaps indefinitely. Scientific simulations, like those from the Max Planck Institute for Astrophysics, have shown just how crucial this cooling mechanism was. These powerful computer models allow us to rewind the cosmic clock and watch as these primordial clouds evolve. They confirm that as the core of the gas cloud became colder and denser, it eventually fragmented into smaller, even denser clumps. It was within these incredibly dense cores, where temperatures and pressures reached unimaginable levels, that the magic of nuclear fusion was about to begin. The amount of material required was staggering. A protostellar cloud needed to gather a mass at least a few hundred times that of our sun for the process to even start. At the heart of one of these dense clumps The pressure became so intense that hydrogen nuclei were forced together. This is nuclear fusion, the engine that powers every star. When hydrogen nuclei fuse, they form helium and release a tremendous amount of energy in the form of light and heat. This was the moment of ignition. A star was born. The first light from these new stars blazed across the cosmos, ending the cosmic dark ages. This initial burst of light, traveling for billions of years, is what telescopes like the James Webb Space Telescope are trying to glimpse, looking back in time to the universe's dawn. But the story of their fuel doesn't end with hydrogen. Because of the unique conditions of the early universe, free from the heavier elements that help cool the gas clouds that form stars today, these first stars grew to monstrous proportions. Their immense mass meant they burned through their hydrogen fuel at a furious pace. A star 1,000 times the mass of our sun would exhaust its primary fuel supply in just a few million years, a mere blink of an eye in cosmic terms. Once the hydrogen in their cores was depleted, gravity would once again take over, crushing the core and heating it to even higher temperatures. This ignited the next stage of fusion, helium burning. In this phase, helium nuclei were fused together to create heavier elements like carbon and oxygen. This process, called stellar nucleosynthesis, is where most of the elements essential for life are created. These first stars were cosmic forges, transforming the simple, primordial elements of the Big Bang into the building blocks of future generations of stars, planets, and even ourselves. The carbon in our bodies, the oxygen we breathe, it was all cooked up in the heart of a star. The number of elements they could create was limited, however. Their massive size led to an explosive and dramatic end. When their fuel was finally spent, they didn't just fade away. They died in spectacular explosions, known as pair instability supernova. These were explosions of such violence that they completely obliterated the star, leaving no remnant like a black hole or neutron star behind. These supernovas seeded the surrounding space with the new, heavier elements they had forged. This enriched material then mixed with the remaining primordial gas, fundamentally changing the recipe for the next generation of stars. So, the secret ingredients that fueled the first stars were a combination of things. It was the simple hydrogen and helium from the Big Bang, pulled together by the invisible hand of dark matter. It was the crucial cooling power of molecular hydrogen that allowed gravity to win the battle against pressure. And ultimately, it was the raw, unadulterated power of nuclear fusion, turning mass into the first light the universe had ever seen. These ancient stellar titans, though long gone, are our cosmic ancestors. They ignited the universe and began the process of chemical enrichment that made our own existence possible. Every time you look up at the night sky, you are seeing the descendants of these first magnificent fires. They were the pioneers, the first sparks in the darkness, fueled by the simplest ingredients in the cosmos and destined to change it forever. Thank you for watching. If you enjoyed this journey back to the dawn of time, be sure to subscribe to Space Repo for more explorations into the mysteries of our universe.